Hi, this is Team 8, and me and my friends have built a language called Lesl. So, my friends include Abhishek Datta, Apur Kainar, Dhananjay Pandit, and myself, Akil Kumar Tota. So, moving on to the flow of presentation, we can see the features of Lesl, working of Lesl, the various tools which are used, and the instructions to build and run the language. So, the features of Lesl. Lesl doesn't require you to declare any data types. Lesl also supports all the various arithmetic operations such as addition, subtraction, multiplication, and division. Lesl also supports various relational operators including ternary operators. Lesl also supports conditional statements such as if, and else. And finally, Lesl also supports looping statements such as while. And the most important feature of Lesl is lazy evaluation. Next, moving on to the working of Lesl. Here we can see the block diagram which describes the various stages that are involved from building till the output is displayed. First, we have the lexical analysis stage, which is done using Python. The output from lexical analysis is being sent to syntactic and semantic analysis, which is being done using Prolog. Next, the output from that stage is being sent to an intermediate code generator, which is again being done using Python. The output from the intermediate code generator is being sent to a runtime environment, which is again done using Python, and final result is displayed on the console. Next, these are the various tools that were used for constructing LESL. They include SWI, Prolog, and Python.
Hi everyone, my name is Abhishek, and I'll be giving you more insight towards the code of our language, how it was built, and stuff like that. So, as you can see, this is tokenizer code. So, it will take a high level code and it will generate the tokens. So, we used Python in here to generate the tokens manually by parsing the high level code, and we generated the tokens. Next, we used Prolog for our for validating the tokens through the grammar and generate semantics and parse tree for that. So as you can see this file syntax.pl. So in this we have defined our grammar. So as you can see all these expressions, Boolean expression, ternary expression, and bool operators and other operations such as else if and all. So we have a loop here which is showing the looping. We are allowing one while, and we are this is our conditional statement. So we are allowing if, else, and else if. So moving to our intermediate code, so this syntax.pl will generate a semantics file that will be containing the parse tree of our high level code. So what this intermediate code will do is it will get the input from there, and it will parse the tree, and it will generate the intermediate code for us. So if I go down and walk you through the main function, so I'm just taking the input in here, and like based on few conditions, like if it's a looping statement or in assignment statement on print statement, and whether it's a condition statement, and accordingly like we have built such a that it should call the subsequent function, and then it should like take each and every variables and numbers, whatever things are there, and generate what you say intermediate code. So this is regarding, so this will generate an intermediate code for us, and later on that intermediate code will be passed on to the runtime environment to generate the output. So to automate everything, there is an environment file which was created by us. So in that, if you can see, we just let me get you through the main. Yeah. So in this, if you see, we are just first taking we are just automated the thing from high level code right from high level code to the generation of the output. So this intermediate file is the file which will be generated for the intermediate code. And similarly for tokens, this file will be, open the file which contains the tokens and things like that. So if you can see here, it's like we have handled for each and every things which are there, which we are allowing as per our grammar. So this is all about the insights and how the things are built internally to generate the output of the code. After me, Apur will be talking about the runtime thing, and he will show you the execution. Thank you, everyone.
Hi guys, my name is Apurva and I'm here to show you some sample codes and how you should run our sample codes. So here is my sample code, sample.lbsl. The only constraint is any sample file should have extension .lbsl unless or else system will give you an error. Okay, so it's pretty simple sample code. There are two variables a and b. Now variables have constraint like they should be started with capital letters, and then you can have any length of the variable, and they can contain any of the values from a to z and 0 to 9, but they should start with capital letters first. Okay, so they are simply a and b. Every statement ends with dot, as in c. Every statement ends with semicolon. In our language, every statement ends with dot. Okay, then there is simple if. Now every if and while loop begins with begin and ends with end, like php. In if, there is simply one statement, that is show a, and after that there is a equals to true. The point I want to make here is every variable can take both boolean and numeric values whenever they whenever you want to assign them, and then simply show a and show b. Now show a is just like print a. We just gave a different function name, show. Now show and show will of course show the value of a and b. Now I'll tell you how to run the program. Here I've created one script named lbsl.py. So python lbsl.py, and then you have to give your program name, that is sample.lbsl. If you run it, it will do tokenization for you, then syntactic and semantic analysis, and then finally, and sorry, then it will generate intermediate code, and then finally it will the environment will run and the output is printed. So this output is because we are running Prolog manually, so this output is coming, but your final output is the value of a is true and value of b is 2. So initially value of a was 1 here, but after that we assigned it to true, so it is showing true. So that's pretty much of it. It's so simple, right? So yeah, I'll show you how exactly your our system evaluates the process. First it will run the tokenizer.py. I'll just open that file. Where is it? Where is it? Sarc tokenizer.py. See, so tokenizer.py, what it will generate is it will just convert your program to different tokens. So Abhishek will explain how tokenizer.py runs, but I'll just show you how tokens are generated. Just a second. Yeah. So tokens.lbsl is the tokens. So see, so these are the tokens. If so, a equals 1 dot b. So it is pretty simple, right? And then these tokens are forwarded for syntactic and semantic analysis. Syntactic and semantic analysis are done in Prolog, so we are using swipl command, and that's the reason this output is coming. Okay, so I'll just show you how semantics are generated. So see, every statement, the for every statement there is encode statement, Okay, there is if, then code block, then if ends, assign it to true, and then at the end, encode print A, encode print B. It's pretty simple, right? So this is uh, how semantic analysis is done. So after semantic analysis, these semantics are uh, interpreted by intermediate code, and intermediate code will be generated. Just a second, where is it? Yeah, so intermediate.ic. Now intermediate code is generated like this. There's it is pretty much like Intel systems intermediate code. Move, JLE, show. This show is customized. We created this statement, but all the others are just like Intel intermediate code. So it is simple, right? Move 1 to T1, 2 to T2, JLE, everything like that. So it is pretty small intermediate code, but it will give you the output. And finally, this intermediate code is uh, submitted to environment, and the environment will run this code and give you the output. So this is your output in front of you. Thank you.
Hey guys, so today I'm going to be talking about the lazy evaluation part in our language, that is LESL. So this is a bit of theory about lazy evaluation in general. Lazy evaluation is also called as call by need. This is an evaluation strategy. This delays the evaluation of an expression until its value is explicitly needed, and this can in turn reduce a lot of our running time by ignoring calculations which are not needed. So we'll move on to talk about how exactly we have implemented lazy evaluation in our language, and that's what the next slide is about. So this talks about the lazy evaluation part in our language. The scope of our language LESL is pretty limited because it does not support any functions, and in turn lazy evaluation also has a limited scope in our language. However, I must mention at this point that our language does support a lot of complex expressions, and lazy evaluation is done in our language in such a way that the value of those expressions will not be calculated or evaluated unless you explicitly ask for it. So just to give you an example, if our program has 100 lines and there is no print statement in our program, that is, the value is not being asked for explicitly, then none of those expressions will be evaluated, and we'll just skip that evaluation, and thus saving a lot of runtime for us and our program. So the next slide, which I'm going to show you in a bit, will talk about an explicit example, a specific example of lazy evaluation in our particular programming language, and let's see how we have handled it. So on the left hand side of the screen is a code which is written in our language LESL, and on the right hand side is the conversion of that code into the runtime environment, which is and basically how we are handling that code in the backend. So the first line that we can see of code is says that the variable a is assigned the value 5. The variable b is equal to 2 times the value that's given for the variable a. Variable c is given a direct value, which is in terms of an expression, that is 15 divided by 3. The variable d is assigned a value of addition of variable a and b, and then the value of the variable c is subtracted from that particular result. So if we look at how we are evaluating it on the right hand side, we can see that a equal to 5 is handled as it is. The value of variable b is not evaluated to 5 times 2, which is equal to 10. The 10 value is not being stored in the variable b. Instead, we are storing the expression 5 times 2 as the value of b. Same goes for the variable c. The value 15 divided by 3 is being stored as it is, and it is not being evaluated further. If we look at the fourth one, the variable value of variable d, it is again an expression which says 5 plus 5 into 2 minus 15 divided by 3, and it is still not evaluated or calculated at this point. The only time when we get the value is when we explicitly ask for it in the line 6, which says hash show d, and then we evaluate the whole expression d equal to whatever that expression is and calculate the value to be 10, and then we rewrite the value of d as 10 instead of that particular expression, so that we don't need to calculate it every time d is called. And here in the last line we say that print a equal to true. This is because our language supports interpreted data types. So our language interprets that a is being reassigned as a variable from the integer value 5 to a boolean variable true. So that's why in the end here we do get the value of a to be true and not 5. So that's about it. Thank you so much.